All right, so hello and welcome to the second week of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being offered by NPTEL. It's been instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm the TA for this course, and I'm currently a PhD scholar at IIT Madras. And like every week, we shall be solving some tutorial problems together and discussing anything and everything related to the course. So without any further ado, let's get started. We will take a look at the first question of today's session, which is a true or false type of question that's that has given us a statement and it's asking us whether it's true or false. So the statement goes as follows. It says that the Reynolds transport formulation relates the control system approach and control volume approach. Is that statement true or is it false? So I would urge you to participate in this. Once you've figured out the correct solution, it would be best if you can, unmute and answer, or if you feel comfortable, you can type in the chat box as well. True. Okay. So let's have a look at the solution. It is indeed true. So that's the primary purpose of the Reynolds transport formulation, to relate control system approach to control volume approach. So in its fundamental form, the Reynolds transport theorem looks something like this. We have the derivative of some extrinsic property n given for a system, which is equated with the control volume side of things, which goes like this. We have dou t of integral rho small n into dv, which is the volume, and this integral is over the control volume, plus we have a integral over control surface that goes like this, rho n v dot dA. This takes care of the fluxes across a control volume. And we have to remember that n is any extrinsic property, and small n is nothing but n per unit mass. So if I, this is all about conservation of n. So if I take n equal to mass, then my small n becomes 1, and plugging these into the Reynolds transport theorem would give me the mass conservation equation, also known as the continuity equation in context of fluid flow. Also, if I take n as momentum, that is mass times velocity, then my n simply becomes velocity, and this gives us the momentum conservation equation. These two together, mass and momentum conservation, these are commonly also known as the Navier-Stokes equations, which governs fluid flow. Similarly, in the context of heat transfer, if I take n equal to energy E and small n to be energy per unit mass, small e, then we will get the energy conservation equation. So any extrinsic property that we plug into this uh, Reynolds transport theorem will help us translate the system laws to the control volume laws, because all my laws, Newton's laws of motion, uh, the laws of thermodynamics, those are all given for the system. But in case of flowing, uh, any configuration where I have something flowing, which is very common in the convective heat transfer context, then we need things for the control volume approach, which is where this Reynolds transport theorem comes in and helps us convert these laws in the system formulation to the control volume formulation. Any questions on this? Okay, so if not, we will move on to the next question of today's session, which is question number 2. and it's asking us uh, again a true or false type of question, which is stating that hydrodynamic boundary layer thickness is much smaller than the length of the flat plate for high Reynolds number flow. So basically, if I have a flat plate like this and I have a flow meeting that flat plate and I have some boundary layer getting formed. So the question is telling that the statement is telling that the hydrodynamic boundary layer thickness, or delta, whether that is smaller or larger than the length of the flat plate, which is L, let's say, for this case, for a high Reynolds number flow where Reynolds number is much greater than 1. Is the statement true or is it false? We have a response in favor of true. Let's hear what others have to say. I would urge everyone to participate here. You can unmute and answer, or you can type in the chat box as well. So what essentially is a boundary layer, first of all? So if I have a fluid which is flowing near a solid boundary, there is a region within which the effects of that solid boundary are felt. So very near to the wall, the flow velocity would be 0, and at a certain distance it would be equal to the free stream velocity, whatever it was. Let's say u infinity here as well. Here it will be 0, and there will be a smooth gradual change in between. So this region, this is known as the boundary layer, and in this case a hydrodynamic boundary layer. In the context of heat transfer or convection in particular, we will learn about thermal boundary layers as well, but as of now the question relates to hydrodynamic boundary layer, and it tells the statement is telling us that whether this is much smaller than the length of the flat plate or not. So mathematically put, given Reynolds number is high, whether delta is smaller than L or not. So if we take a look at the solution, it is indeed true. So what happens is that this boundary layer, this is actually very thin. So in case of aeroplanes moving close to Mach number even, so for few meters of the aerofoil or the wingspan, the boundary layer thickness is usually a few millimeters only. But then again, even that small region of a boundary layer creates a lot of consequences, which becomes important. And that's why the study of boundary layer is so much important. So in case of fluid flow, the boundary layer dictates the drag and lift on the aerofoil. In case of convection, we will see that the temperature gradients within the thermal boundary layer, they will dictate the rate of convection out of that solid boundary. So these are important nonetheless, in spite of being very thin. Okay, any questions on this? If not, we will move along. We'll move on to question number 3 now, which is again regarding laminar boundary layer flow. So similar to what we saw earlier. So again, I have a flat plate like this. This is my x-axis. This is my y-axis. I have some flow coming in with a uniform velocity u infinity, and a boundary layer develops on top. And the question that is being asked, and also the boundary layer thickness is given by delta, y equal to delta. So this part is y equals delta. So the question is asking us, there are a few options given. It is asking us which of the following boundary conditions, the options are different boundary conditions. So which of the following boundary conditions is not valid for laminar boundary layer flow over a flat plate along the x-axis? So statement 1 says that at y equal to delta, u equal to u infinity. Is this true or not? Statement B says, or option B says, at y equal to delta, dou u dou y is equal to 0. Is that true or not? And also statement 3 says at y equal to delta, the double derivative of u is 0. Is that again true or false? Or statement D says that none, meaning that none are not valid, which means all are valid. Okay, so we have a response in favor of option D. That is, all of them are correct essentially. So let's go through these statements one by one. So the first one, I have my boundary layer that looks something like this. I have u infinity here, I have 0 here, and there is a gradual change over here. So at y equal to delta, u does become equal to u infinity. That's by definition. So delta is defined in a place where u becomes equal to u infinity. So statement 1 is correct. Statement B says dou u dou y is 0. There is this gradient, this slope at y equal to delta, that also becomes 0 because it cannot increase or decrease further than u infinity. It just becomes u infinity and remains constant over there. So dou u dou y is also equal to 0. And if dou u dou y is 0, we know that if I derive it once again, the second derivative of u with respect to y, that also should be 0, right? So all these three statements are valid statements. So none of them are not valid. So D should be the correct answer, and it indeed is. So good. So far so good. Any questions on this? Okay. So if not, we will keep moving along. We'll move on to question number 4 now, which is asking us which of the following conditions are required for formation of thermal boundary layer. Or let's stick to which of the following condition is required. So I have only one condition that is required among these four. So is it statement A or option A, slender body without flow separation, option B, high Reynolds number, or statement B or option C, high Prandtl number, or is it option D, that is all of the above? Okay, so we have a quick response in favor of option D. Let's have a look at the solution. It is indeed option D, all of the above. So why is that? So first of all, I need a slender body without flow separation so that the flow stays nicely attached to the body. Now in case I had a body like this, let's say a bluff body, something like this. So in this case, if flow is coming in, so the flow would separate out like this, and we won't get a nice boundary layer. There would be all sorts of mixing and most probably even turbulence going on. So the absence of flow separation is actually needed for the formation of a thermal boundary layer. Then apart from that, I need a high Reynolds number so that for low Reynolds numbers, the boundary layers would be thick. So a boundary layer would definitely be formed. So let's look at the case of a flat plate like this. In case Reynolds number was low, I would get a thick boundary layer as compared to a thinner one. And thicker boundary layers are usually not stable, and they cause mixing with the free stream velocity, and thus we won't get the formation of a boundary layer properly. And also high Prandtl number. So Prandtl number is basically given by this nu by alpha. If Prandtl number is high, that means nu is greater than alpha, in which case that is so if the momentum diffusivity is high enough, then only we will get some thermal boundary layer, otherwise it won't form in the first place. So that's why all these three conditions are required for the formation of a thermal boundary layer. Any questions on this? All right, simple enough. We will keep moving along. We move on to question number 5 now, which is asking us that Peclet number is a product of which of the two following dimensionless numbers. So I'm telling that the Peclet number PE is a product of two dimensionless numbers, A and B. Now, what are these A and B? Is it option A, Bond number and Fourier number? Option B, Reynolds number and Prandtl number? option C, Grashof number and Nusselt number, or is it option D, Nusselt number and Prandtl number? Once again, we have a very quick response in favor of option B, which is indeed the correct one. So Peclet number by definition is given as a product of Prandtl number and Reynolds number. So if we try to simplify it, Prandtl number is given by, as we saw in earlier, nu by alpha, and Reynolds number is given by u l. L is the length scale by nu. So nu cancels out and we get ul by alpha, where u is the free stream velocity, L is the characteristic length scale, and alpha is the thermal diffusivity. So what exactly is Peclet number telling us in general? So this is in context of heat transfer. Peclet number is also defined in the context of mass transfer. What does it mean in general for any context? Any guesses? So what it actually means is that it's the ratio of any quantity. Yes, mass diffusion by heat diffusion. Uh, so is the transport by advection or convection in case of heat transfer divided by diffusion. So if Peclet number is high, very high in some case, then it's the advection or the bulk motion of the fluid which carries some quantity of interest that is dominating over the diffusion of that quantity, which happens slowly. Whereas in low Peclet number cases, it's the diffusion that is the dominating characteristic or the dominating phenomena that's going on. So in that way, Peclet number is a very important quantity. Okay. Any questions on this? If not, we will keep rolling. We'll move on to another true or false type of question. Lots of true or false type of questions in this one. Okay, so this week basically. So we are looking at now, the statement says that the normal pressure gradient, the normal pressure gradient is comparable to the axial pressure gradient while deriving the boundary layer equations. Is that true or is that false? Once again, this is my configuration, a flat plate and a boundary layer forming over it. So the normal pressure gradient, so if I define my y and x in this manner, so the normal pressure gradient is in this direction. So dou p dou y, and axial pressure gradient is in this direction. So dou p dou x. So the question says that while deriving the boundary layer equations, do we take these to be comparable or not? That is, dou p dou x is of the same order of dou p dou y or not? So the answer is false, right? Why is it false? What should have been the correct uh, relationship between axial pressure gradient and normal pressure gradient? So if they are not comparable, one is larger than the other. Which one is larger in this scenario? Any guesses? I mean, you can take a guess. Like, you don't have to be perfectly correct. We are just discussing things. So it's actually, the main the main fluid flow is going on in this direction, so there should be a sufficient pressure gradient to really drive this flow, whereas the in the axial direction the flow is very low, so it doesn't really it isn't really significant. So it's the actual pressure gradient which is much larger than the normal pressure gradient. Okay, any questions on this? If not, we shall keep rolling. We'll move on to a numerical type question now. Question 7, sorry, which is asking us to consider once again a boundary layer over a flat plate. So consider steady parallel flow of air, rho equal to this much, nu equal to this much, over two parallel flat plates separated by a distance of 3 millimeter. Okay, so it's not just one flat plate, we have two flat plates like this. And we have steady parallel flow coming in. So essentially what will happen is that my boundary layer will grow from this side, it will grow from this side and meet at some distance, right? So the air has a temperature and a free stream velocity of so much and so much. So both T infinity as well as U infinity are given. Find the distance in millimeter from the leading edge. So this is the leading edge. I'll call this my origin. X starts from here and this is Y. So find the distance in millimeter from the leading edge at which the boundary layer merger would occur. So how to geometrically define that? So basically these two parallel plates, they are told to be separated by a distance of 3 millimeters. So this entire distance is 3 millimeter. Now given these are symmetric, so the boundary layer would have to develop till a thickness of delta, which should be half of this. So 3 by 2 millimeter should be the boundary layer thickness. Now at what distance would that occur? What would be the x where this delta becomes half the uh, separation width, and therefore the boundary layers would merge together? Do you want to take a shot at solving this problem? We have given a hint as well that delta by x should be equal to 5 over square root of Reynolds number. So take a shot at solving this problem, and you can either type in the chat box or you can unmute and answer as well. There's no hurry, take your time. So this equation has to be used. This is the main equation that relates delta to x. We have found out what delta should be. We just need to find out at what x that delta is achieved. So basically, let's start with this equation. Delta over x is equal to 5 over Reynolds number of x. And Reynolds number of x is given by u infinity x over nu. Sorry, I'll just write this nu in a better way. Yeah. So 5 over u infinity into x, and the nu I am shifting to the numerator side. So delta over x equal to this. If I take only x, uh, then okay, I'll take this x on that side. So okay, I'll just transfer this x to the left hand side. So this becomes root x by x, which is x power minus half, and that should be equal to 5 over delta into nu over u infinity. Wait, I see you gave an answer. Let's take a look at that. 141.6. Yeah, I think that's close to the correct answer. Yeah, the correct answer is 141. Good. So let's go back to the solution once again. So, okay. So this was my equation. Now x should be equal to, then I would take, uh, okay, I would flip it and square it. So this becomes delta by 5 squared, and this becomes u infinity by nu. So my delta has to be 1.5 millimeters, right? So 1.5 into 10 power minus 3 squared divided by 5 squared, that is 25, into u infinity. U infinity was given as 25 meters per second, and nu was given as 15.89 into 10 power minus 6. So if I plug in all these values, I should be getting uh, something close to this. Sorry. Yeah. So I hope you followed the same procedure. Is that okay? Any questions, doubts, remarks on this? Okay. So let's move along. We'll move on to question number 8 now, which is once again a numerical type question, which is asking us that for flow of fluid over a heated plate. Now, it's not just a flat plate, it's a heated one. The following fluid properties are known. Density is given, kinematic viscosity is given, specific heat is given, thermal conductivity is given, the hydrodynamic boundary layer thickness at a specified location on the plate is 1 millimeter. So delta H, or delta H hydrodynamic boundary layer, I call this HBL, that is given as 1 millimeter. This can be called as simply delta as well. That's the common terminology. Whereas the thermal boundary layer location in the same location is what? The thermal boundary layer, delta sub T. Is it option A 1.8, option B 2.5, option C 0.6, or option D 0.4? There's no hurry, take your time, and once you have figured out the solution, you can type in the chat box or you can unmute and answer as well. So basically, uh, we first have to see what's the Prandtl number, because the relationship between delta and delta t is usually given as, the Prandtl number to the power some m, and the value of this m depends on the value of Prandtl number. So if Prandtl number is much greater than 1, mm, is being greater than 1 means m equal to 1/3, I guess, and Prandtl number less than 1 means m equal to half. Am I right? I'll just check once. It could be the other way around as well. This is correct, right? Okay, so going by that logic, I'll have to first check Prandtl number. So Prandtl number is given by nu over alpha. Nu is given over here. This is my nu, and alpha has to be found out. Alpha is k over rho Cp. Alpha isn't explicitly given, but all these three values are given. So k is 5, uh, rho is 0.25, and Cp is 1.6 kilojoule per kg Kelvin, so 10 power 3. Can you help me with the calculation? What is the number here for alpha? 0.125. Okay, it's 0.0125. So it is less than 1. So we'll have to use this relation where m equal to half, right? So my delta over delta t, this becomes Prandtl number over half. So delta is given, delta I know 1 millimeter. I'll keep this in millimeters only because delta t is also needed in millimeters. It's only the ratio that matters. And equal to, okay, so let's find out Prandtl number as well. Prandtl number is 0.002 divided by 0.0125. Okay, so this was wrong, sorry. So how much is this? 002 over, I think, 40, right? Or no, sorry, uh, 0.16. Oh yeah, 8 into 2, yeah. So 0.16 is, so Prandtl number is less than 1. We will use m equals half. So 1 millimeter over delta t in millimeter should be equal to this Prandtl number, that is 0.16 to the power half, which is zero point 0.4, I guess, right? So delta t should now be 1 over zero point 0.4, that is 2.5, right? So option B should be the correct answer. Let's check. Yes, option B is the correct one. Okay, so this is the procedure. Any questions on this? Simple, right? You just needed to check the Prandtl number. On that, the value of m would depend. Okay, cool. So let's move along. We'll move on to question number 9 now, which is asking us that the conditions for a Stokesian fluid is what? Option A, the relationship between stress and strain rate is linear. Option B, the volumetric strain rate is 0. Option C, the fluid is homogeneous and isotropic. Or option D, none of the above. Which one is the condition for a Stokesian fluid? A and C. Okay, so that's not an option. We'll take a look at the solution. It's actually only C. The fluid just has to be homogeneous and isotropic in order to be called Stokesian. Yeah. So let's go through the other ones. So if the relationship between stress and strain rate is linear, what do we call that fluid? A Newtonian one. Good. And what about a fluid where the volumetric strain rate is 0? Volumetric strain rate means essentially uh, dou u dou x, yes, dou v dou y. Sorry, uh, just plug in my charger. Give me a moment. Yeah, sorry about that. So dou v dou y plus dou w dou z, basically this is the volumetric strain rate, and this being zero basically boils down to, you know, an incompressible fluid. So volumetric strain rate, or simply the divergence of velocity, that's just a fancy way of saying how much is the expansion of a fluid. So if the expansion is zero, that means it is incompressible, right? So these are the things. Any questions on this? Pretty simple, right? Yes. Incompressible flow, but yeah, truly there are no incompressible fluids. It's just the flows which are incompressible in certain situations. But theoretically, there can be incompressible fluids as well, right? Where no matter how much pressure you apply, they won't compress. Okay. So moving on to the last question. This is asking us now that which of the following non-dimensional groups, should be groups, is not present in the non-dimensional form of the energy equation? Is it option A, Nusselt number, option B, Eckhart number, option C, Reynolds number, or option D, Prandtl number? So yeah, option A, Nusselt number. So it's kind of counterintuitive since Nusselt number is so important for convective heat transfer, yet it doesn't appear in the non-dimensional form of the energy equation. So if I remember correctly, it's only the Eckhart number and a Peclet number also appears. So basically, Prandtl and Reynolds mixed together. It's the Nusselt number that doesn't appear. So the correct answer is again option A, Nusselt number. So I'm not deriving this. We could derive the non-dimensional form from the dimensional form and show that uh, the other three non-dimensional groups show up there, but Nusselt number doesn't show up. Is that okay? Okay. So that was the last question of today's session from my side. Thank you for participating. See you again next week. So if you have any questions, you can always ask. These sessions are for that.